What I would like to do here is to go through a few problems that are actually part of our study questions and give you a couple of hints on how these problems might be solved. Most of these use the icebox, and we're going to see how that works. There's a couple of these we're going to look at a new idea called the reaction quotient that will let us know where we are with respect to equilibrium. And then finally, some of these are just little algebra tricks that we can do to solve these icebox problems. Now, from our study questions, problem number 4 is the first one we'd like to look at. And reading through, we say chlorine molecules will dissociate into high temperatures into chlorine atoms. So chlorine molecules, chlorine atoms, at 3,000 degrees Celsius. Now, a lot of these problems talk about the temperature. And usually you don't need that temperature. It's just proper to talk about the temperature because the value of K is dependent on the temperature. If you have a different temperature, you'd have a different value of K. So it'd be proper to say at 3,000 degrees, the Kc is 0.55. At a different temperature, it'd be a different value. Now, if the partial pressure of chlorine molecules is 1.5 atmospheres, calculate the partial pressure of the chlorine atoms. Now, I can see, because I've been doing this forever, that if I were to have a problem where I say, here's my Kc, so let's go ahead and write that, equals the concentration of Cl squared over the concentration of Cl2, and there's nothing funny about this, equals 0.55. And somebody asked what the units are. I would say it's concentration over concentration, so I would say it's going to be molarity, moles per liter. I can see that here I have 3 variables. I've got this guy, I've got this guy, I've got this guy. And so if I tell you 2 of the 3, you can find the last one. So we're saying that the chlorine molecules, be careful, we're talking about chlorine molecules, so these guys down here is 1.5 atmospheres, so we can calculate this one. So if I know 0.55, I know this value, and I can find the other value. The problem here is they're not telling me the concentration of chlorine molecules. They are giving me the pressure. So what I really need is Kp. Now, in each of these problems, I don't want to go through and solve them because that's your job. Plus, you have the answers in your study guide book. But I want to say, what do you need to think about for each of these? So I really want to do this Kp expression. And to solve the Kp expression, what I'm going to do is have to go through and do Kp equals Kc RT delta N. Okay, so you can see that I have the Kc value, I know that. Okay, R, that's a constant. And you should just have that tucked away, the 0.0821 liter atmospheres per mole Kelvin. And since we're doing kPs, we can do atmospheres. Okay, T is temperature in Kelvin. So here we do need our temperature, it turns out. So we can't use 3,000, we have to add 273, so 3,273 Kelvin. And the delta N is the number of product moles minus the number of reactant moles, so of gas. So 2 moles of gas minus 1 mole of gas, so N is equal to 1. 2 minus 1 is 1. So we know all our variables, and we can substitute those in, get a value for Kp. And if I know Kp, and I'm told the pressure of that, then I can find this one. And again, don't forget that this little guy is squared. That's the kind of little mistake that's very common to make when you get everything done. You say, okay, I know what I'm doing, and you forget to square, you get a totally wrong answer. So when we get all done, then remember that we are using Kp expression. We're using our equation, Kp equals Kc RT to the delta N, and that's just to get our Kp value. And then if we know a couple of numbers, then we can find whatever the missing value is. So that's problem 4. Problem 5. Okay, we can see here that we have 0.5 moles of hydrogen gas, 0.5 moles of iodine, 0.75 moles of hydrogen iodide in a 2-liter vessel. calculate the concentration, that's important, of all the three substances at equilibrium. Now, an important idea is anytime we have these problems, a lot of times students get very nervous. So one thing you can do is do the three things that you probably are going to need to do for an equilibrium problem. And one is to write down the equation. And in this case, the equation is given to us, but sometimes it's not going to be given, so it may be implied. So we're going to see several different K values. So if I said something like the Ka, that's going to be the acid equilibrium, that would imply an equation. If I say the Ka of acetic acid, that implies an equation. So write down the equation, do an ice box. In the ice box, we have a column for each chemical that's in here. And the other thing we want to do is to probably write the K. And are we given a K? Yes. So here's the Kc is 2 times 10 to the minus 2. So let's just write that down here, Kc. Now the concentration of Hi squared over H2 times I2, and that equals 2 times 10 to the negative 2. So that's the useful information, the equation, the icebox, and the equilibrium expression. Write those three things down. Now if you are nervous, then just writing those things down will kind of give you something to do for a few moments and give you a chance to calm down and get ready to do the problem. Now, here comes an issue, and that is, it says calculate the concentrations of all three substances. So we're going to want all three of these values down here. And we want them as concentrations, but we're given values in moles. Now that's not tough, okay, because we know the liters, so we're just going to take moles divided by liters. But in an icebox, you can do this using moles, and you can do this using molarity. And if you're talking about a gaseous system, you can also do it with pressure, like torr or ATMs. That will work because the partial pressure of the gases is proportional to its concentration. The only thing you cannot use is grams. So we could start by saying 0.5 moles of hydrogen, or we could say I have 0.5 moles of iodine and 0.75 moles of hydrogen iodide, and we could work out our icebox, and when we get done we have to divide by 2 liters because it's asking for concentration. Now if you're the kind of person who forgets to do a little step like that, you're going to end up with a totally wrong answer, so it might be good to go ahead and put that in early and get values that are in molarities to start with. That way when you're finished, your values will be molarity. So that is a really, really good idea. Now, I'm going to go back. So this is 0.5 over 2, so this can be 0.25 molar, 0.25 molar, and 0.375 molar. And this is very, very messy, so let's go to another page. So I'll recreate my icebox. And I'm going to put in my values. So this one we said was 0.25 molar, 0.25 molar, and 0.375 molar. Now, we've run out of numbers, so now we're going to use letters, and we're going to say something in terms of, well, if this equilibrium shifts to the right, that means we're going to make some of this chemical, and we're going to use up some of these two chemicals. But if it's shifting to the left, then our reactants are going to be plus values, and the product would be minus. So we have to figure out, does it shift to the right or does it shift to the left? And that's where we get a whole new concept here called Q. Now for Q, it's exactly the same. Q means test quotient, by the way. It's exactly the same setup as our K. So I would say concentration of Hi squared, almost forgot that, over concentration of H2 and concentration of I2. Now, Q is different than K because if I have my K values, I'm actually using equilibrium values. I'd use my values from down here. But if I put in my values from my initial values, then this is going to let me figure out whether I need to shift to the right or shift to the left to reach equilibrium. So let's get our numbers first. 0.375 squared over 0.25 times 0.25, so that's squared as well. I believe that comes out to be 2.25. Now, the K is the products divided by the reactants concentration. So just in a general sense, we can look at this and say, okay, my Q is greater than my K, because remember that for K, the value was 2.0 times 10 to the minus 2, so 0.02 is my value of K. Well, this is much, much larger than my value of K. So if Q is greater than K, that means my products is much larger than my reactants. More is larger than what it would be at equilibrium. So I have too many products. Now if I had substituted in my values and I had gotten 0.02, 2 times 10 to the minus 2, then that means I'm already at equilibrium. But here I have too many products, so what can I do? I can shift from my products to my reactants, so I'm actually going to go from right to left. So my, pick a color here, I'm going to shift this way. So my scoopy arrow I had was actually the wrong direction, so I'm going to go that way. So I'm going to use up some of this chemical, and I'm going to make some of this chemical and make some of this. Now, these X's I'm going to put in have to match my 1 to 1 to 2 ratio, so I'm going to call this plus X, and minus 2X. I hope you can see that, minus 2X. Now, the values in my equilibrium box are going to be expressions, so this will be 0.25 plus X, 0.25 plus X, and 0.375 minus 2X. Okay, not too troublesome. Now, we're going to go back now and use our K value. And so I'm going to say I know that K equals, okay, the same thing I have for my Q, so concentration of HI squared over my concentration of H2 times concentration of I2, and I'm going to substitute in my expressions. So I have 0.375 minus 2X squared over 0.25 plus X times 0.25 plus X, so that's going to be 0.25 plus X squared, and that equals 2.0 times 10 to the negative 2. Now, I'm about to leave you here. This idea now, all we have to do is solve, and the trick is that since I have squared and squared in my numerator and denominator, all I have to do is take the square root of both sides of my equation. So radical this side equals radical this side. Now that's going to cause my right side to be a number. Okay, so this is a 2 times 10 to the minus 2, square root of that will be about 1.89 times 10 to the negative 1. And I'm going to have 0.375 minus 2x, 0.25 plus x, and it's a matter of simplifying this expression, getting the x's together and all that. Okay, so that's the algebra that you are required to do. Now I have one last thing to mention here, and that is the actual question says calculate the concentration of all three substances at equilibrium. Okay, so we want these three values down here, so we don't want to just solve for x. So we can solve for x, and once we get our value of x, we need to go back and substitute back into our expressions to get values for x. So it'll be 0.25 plus our answer, 0.25 plus our answer, 0.375 minus 2 times our answer before we actually get the answers we want. So that's a major hint, and that is every time you solve a problem, go back and look at the question really quickly before you move on and decide, have I actually answered the question? And that's a very, very important tip for the AP test and for the regular test. Okay, now it's going kind of slowly, so let's look at number 7. Number 7 says we have 2 moles of carbon disulfide, 4 moles of chlorine placed in a 1 liter flask. Now the fact it's in a 1 liter flask means moles and molarity are going to be the same value. The following equilibrium system results. At equilibrium, the flask is found to contain 0.3 moles of carbon tetrachloride. What quantities of the other components are present in this equilibrium mixture? Well, let's do the ice box. Now, if they say what quantities, then that is a little bit vague. So since my values to start with are moles, then I'm going to keep my answer in moles and report my answer in moles. So if they really wanted grams, I think they should have said grams. Now, from the problem, 2 moles of carbon disulfide, 4 moles of chlorine, I filled those in, and implied, since they didn't say they added any of this, or added any of this, that these two are 0 moles. So 2 moles, 4 moles, 0, and 0. Now the last little tidbit they give us is that the flask is found to contain 0.3 moles of carbon tetrachloride, this guy. So this is 0.30 moles. Now I'm not going to put any more units in because it's getting cluttered already. So you can see what's going to happen is if I started with 0 and I ended up with 0.3, then I must have made 0.3 moles. Now if I started with 0.3, if I have 0.3 moles here, as soon as I get anything in this change row, then I can fill in the whole row because it's going to be in this 1 to 3 to 1 to 1 ratio. So this number is going to be 0.30 moles. This number is going to be 0.30 moles. And since this is 3 times that, this will be 0.90 moles. Now if I'm making 0.30 moles of carbon tetrachloride, I must also be making 0.30 moles of S2Cl2. I must be using up 0.9 moles and using up 0.3 moles of my reactants. And that's when I draw this, I try to draw a double arrow here, a double line under my double arrow to remind me that one side we're going to have positive change, the other side will be negative change. So we go back now and say if I started with 2, I used up 0.37, you can tell me this value. If I started with 4 and I used up 0.9, you can tell me that value. And if I started with 0 and I made 0.3, you can tell me that value. And those are my 3 answers for my problem. Okay, problem 8. Similar. Okay, so we have 3 moles in a 2 liter container. So we're going to put those two together, and that's where we get the 0.15 molar. So 0.15 molar, 0.15 molar. Now notice what I've done, and that is carbon is a solid. And since it's a solid, then it does not enter into my expression. It's not going to enter into my calculations. And you might want to keep track of it just in terms of, do I have the chemical I need in order to do this reaction? But it turns out most of the time we can ignore it totally. So I just cross out the solid in my ice box and we just move on. Because we didn't say we added any water vapor, then I'm going to say that implies that this is 0 molar up here. So I have my first numbers. Okay, next we have our Kc expression, okay, because it tells us that the constant is 4.0. So I can write my expression here, no surprises. Okay, now I say if I started with 0, I end up with x. If I 1.5 divided minus x will be these expressions, and I substitute those in here. Now you can see what happens is it's not x squared over squared. I cannot do my square root both sides. In fact, there's really nothing about it. I'm going to have to do the quadratic equation here. So I'm going to multiply, I'm going to just go to the next page. So I started off Here's the expression. I just copied this from the other page. And now I'm going to move my denominator from one side to the other side. I'm going to go through and I separated it out into 1.5 minus x times 1.5 minus x. I did FOIL from the old days to get these values, and it's still times 4. Now I multiply my 4, so 4 times 2.25 is 9, 4 times 3, negative 12, 4 times 1, 4 here. And finally, I have to get that x combined with my other x's, so subtract x from both sides. So I have this equation, which I rewrite into standard quadratic equation. Now, I don't have a calculator that will do the fancy solving. I just used a computer program and it found, I Googled quadratic solver or something like that, quadratic calculator, and I found a bunch of websites where all you do is substitute in A, B, and C, and it tells you the roots. Because this is squared, we actually end up with two values, and one of those values should not make sense. Mathematically, it solves the equation, but it just doesn't make sense. So I have 2.25 and 1.0. So let's go back and look at our problem. Let's pick a new color. Now what we have going on is, if this is x, if that's 2.25, that can't work, because I only have 1.15 chemical, I can't subtract 2.25. So I cannot get a negative value down here in my concentrations. So I know that the 2.25 value, that just does not make sense, and that's okay. So 1 is my answer. Now, the question is, what is the equilibrium concentration of water? And that is my x, so I know it's 1.00 molar, and that's the number I report for my concentration of water vapor. Now the last problem I want to work on in this part of the tutorial, because I'm going to go back and finish this up with a second tutorial, and that is question number 9. And this is easy and difficult, and that's why I put the letter D here in italics, because this is a difficult part of our problem. But A, B, and C is very straightforward. It says, what is the value of the reaction quotient? So we're talking about pressures here, and it gives us a value for our, where did it go? Here it is, for our case of P. So we're going to do everything in pressures. So the Q here is the partial pressure of NO squared times the partial pressure of Cl2 squared, not squared, just to the first power, divided by NOCl quantity squared. So those three values. Using the numbers on the problem, I put in 43 squared, 23 over 675 squared, and we get a value of 0.0933. So we can see what's happening is Q, that we just calculated, is greater than the K, which is 0.6. So I have 0.09 compared to 0.06. And so since I have Q is greater than my K, then right now I have too many products. Because remember, this is products over reactants, concentrations. And if my Q is too large, I got too many products. So I'm going to have to change my products into my reactants to reach equilibrium. So my answer, what is the value of the reaction quotient? 0.0933. Is the mixture at equilibrium? No, because if it was, it wouldn't be 0.0933, it would be 0.060. And in what direction will the system move to reach equilibrium? I have too many products, so I'm going to switch to the reactants, change some of my products into reactants to reach equilibrium. Now the last portion of this is, you could do an icebox for this equation. Now if we do, and if you try it, you're going to find out that we have a mathematical expression with f for all three values, and when you substitute them back into the expression, we're going to end up with x cubed rather than just x squared. So for that kind of problem, what you really need to do is to go back and do a guess and check. Just keep putting in values and putting in values for x until the Kp is close to 0.06. And this book even suggests you could do this as a Excel spreadsheet. Now, this would be way beyond what we would ever do in our class, okay, way beyond what we would do certainly on the AP test, because you're not going to have an Excel spreadsheet to do there. But this is a valid thing to do. If you have an equilibrium that you're trying to study, then one thing you might want to do is to just guess and check until you can find values of X that would work. Okay, that ends this part of there. I'm going to come back for a second part where we're going to do 10, 11, 12, and 13.